Hello everyone, how are you doing? I hope you're great. This is part 4 of the hoverboard series, and in this part we will create the movement for the hoverboard. So as you can see, now we can move the hoverboard around freely in the world. As you can see, it's pretty stable because of the last video that we stabilized the hover. So this is what we're gonna build on this video. But before, if you do like this video, please hit the like button and subscribe so you don't lose any new content. And now we have members on the channel. So if you want to support me and have early access to new videos, feel free to join on the membership. I appreciate your support. So without further ado, let's start. Okay, so I'm here in the hoverboard blueprint, and first let's organize these functions that we created in the last video. So the apply linear damping, apply angular damping, and limit rotation I will put in the stabilization category. So let's just select this, and here in category let's just select stabilization. Let's do the same for the other ones. So the apply angular damping and limit rotation as well. And there you go. Okay, so to do the movement, first we need some variables. So here in variables, let's create a new one. I will name this forward acceleration, like this. Let's set the type as float. Let's create a new one for the backward acceleration. A new one for the forward force. Another one for the backward force, and then we need two more for the turn acceleration and turn force. So let's just create those here. Turn acceleration and turn force. And there we go. So now we have all the variables that we need to do the movement. Let's just put those variables in a movement category. So let me just select the first one here, and here in category let's type movement, and now we have the movement category. So to put the other ones in the same category, we just need to drag the variable in the category like this. So let me just put all these here in the movement category, and there we go. Now we have all the categories that we need. We can start calculating the forces. Okay, so let's create a new function to calculate this. So let's go here to functions, let's add a new one, and I will name this calculate movement force, like this. So let's implement this function now. Okay, so basically I will do this the same way that we did with the hover. So I will use Newton's second law of motion that says that the force is equal to the mass times the acceleration. So let's start getting the mass. So first we need the mass of the hoverboard. So let's drag the hoverboard here in the graph, the static mesh in the graph. And from this we can type get mass. So now we have the mass of the hoverboard, but we need the mass of the character as well, of the current driver. So let's drag a reference for the current driver variable. Just hold Ctrl on the keyboard and drag to get the reference like this. And from this we can get the character movement, because this is a character variable. So the type of this variable is character, so we can get the character movement. Let's drag from the variable like this, and here just type get character movement, and if we scroll down we will see this value here, get character movement. Let's click on this, and from the character movement we can get the mass. So just drag and type get mass. So now we have the mass of the character as well. Let's just add those together. So from the mass here of the hoverboard, let's drag and let's type plus to get an add operator. And let's put this in the second pin, let's put the character mass. Let's connect here. And now we just need to multiply this with the acceleration that we want. So first let's do with the forward acceleration. So let's drag this and let's type multiply. So we have the operator here. And in the second pin, let's connect the forward acceleration. Let's drag this in the graph and connect here. So basically now we have the force in newtons, so we need to convert this to centinewtons, as I said when we calculate the hover force, right? So we need to multiply this by 100. So just drag here and multiply by 100 like this. So now we have the final forward force to apply in the hover. So let's set this in the forward force variable. So to set this, hold Alt on the keyboard and drag the variable to create a set node like this. Let's connect the execution pin. And of course, the new value of this is this calculated here, this force that we just calculated. And there we go. So now we calculated the forward force. Let's do the same for the backward force. To calculate the backward force is basically the same. We just need to multiply this mass that we are adding together here with the backward acceleration. So let me just put this here up so we can drag from this add here. So let's just drag and let's type multiply again. But now in the second pin, let's put the backward acceleration. Let's just drag this in the graph. And there we go. Now we have the force in newtons. We need to convert to centinewtons. So let's multiply this by 100 again. So let's just type 100 here in the second pin. And there you go. Now we have the backward force as well. We just need to set this on the backward force variable. So just hold Alt on the keyboard and drag to the graph to create the set node, connect the execution pin. And now we have the backward force here. And there we go. So now we are calculating the forward force and backward force. Let's calculate the turn force. Okay, so the turn force will basically be a torque to apply in the hover. So to calculate this torque, first we need to get the inertia tensor of the hoverboard. To do this, let's drag the hoverboard in the graph like this. And from this, we can type get inertia tensor. And here, as you can see, we have the inertia tensor. We just need to multiply this with the turn acceleration. So let's drag from this and multiply with the turn acceleration. So just get the variable and connect in the second pin. And this will give us the vector, but we only need the magnitude of this vector, so basically the length. So to get this, just drag from the vector here and type length. So we have the float here that represents the length of this vector. So this is basically the torque that we need to apply in the hoverboard. So let's set this value in the turn force. Let's just hold Alt and drag the variable in the graph like this. Let's connect the execution pin. And now let's connect this value here in the turn force like this. And there we go. So this is basically it. This function will calculate all the forces that we need to move the hoverboard, to control the hoverboard basically. So now let's call this function. So let's go back to the event graph. Let me just close these other functions here that we are not using at the moment. So let's go back to the event graph and we will call this function in the initialize forces event. So after calculating the hover force, let's call the calculate movement force here. And this event is being called when we enter in the vehicle. As you can see, when we enter, we call the initialize forces. So this event here will calculate the hover force and then calculate the movement force now. So there we go. Okay, so let's create the function that will apply the movement in the hoverboard. So here in functions, let's add a new one and I will name this apply movement like this. And this function will need one input. So here in inputs, just add one and I will name this move input. And the type of this will be vector2. So just change the type here to vector2, this one here. So basically this move input will be the same that we are using in the character. So I will use the same mapping, right? So let's compile and save. And now let's implement this function. Okay, so let's start by applying the torque. So basically I want to turn the hoverboard by pressing A or D in the keyboard. So basically we need the x-axis value of this move input. To get this, just right click on the input and click on split struct pin. So we have the x and y axis here. So we need the x value for this. But first let's get the direction that we need to turn. So basically the axis to rotate the hoverboard. To get this, let's drag the hoverboard in the graph. And from the hoverboard, let's type get up vector. So basically to turn the hoverboard, we need to apply the torque in the up vector, right? So now we just need to multiply this here with the turn force. So here in the variables, just drag the turn force variable in the graph like this and connect in the second pin. So basically we are multiplying the get up vector here. So the up vector of the hoverboard, this is the local up vector of the hoverboard, right? We are multiplying this with the turn force. And now we just need to multiply this with the X input. So basically when we press A on the keyboard, this X here will be -1. So this will basically invert the rotation here. And when we press D, this X value here will be 1. +1, so this will basically be the same, right? And of course, if we are not pressing, this will be 0, so basically anything multiplied by 0 is 0, so we will not turn the hoverboard, right? So now let's just multiply this by the X input here, like so. And now we just need to apply this as a torque. So to apply this as a torque, let's drag the hoverboard in the graph like this. And from this we can type add torque, and let's use this one here, add torque in radians. Just click on this and connect the execution pin, and of course the torque to apply is this one here, so just connect in the torque input, and there we go. So basically now when we press A or D in the keyboard, we will rotate the hoverboard in the up axis, right? Okay, so to apply the forward force or the backward force, first we need to know if we are trying to go forward or backward. So basically, because I'm using here the same mapping that we are using in the character, this input Y here will basically be W or S in the keyboard. So when we press W, this input Y here will be 1, +1, and when we press S on the keyboard, this input Y here will be -1. So using this information, we can know if we're trying to go forward or backwards. To do this, we just need to drag from this input here, and let's type greater. So we have the greater operator here. Let's just click on this, and in the second pin, let's leave as 0. So let me just add a reroute here. So basically, if this is true, that means that we are trying to go forward, because the input Y will be 1 if we press W, right? So it is greater than 0. And of course, if this is not greater than 0, that means that we are pressing S on the keyboard, so the input Y is -1, so we are trying to go backwards, right? So now let's just add this in a branch here. Let's connect the execution pin. And again, basically, if this is true, we will apply the forward force, and if this is false, we will apply the backward force. So let's do this. Okay, so let's deal with the false first. So basically, if this is false, that means that we need to apply the force in the backward direction. So first, let's get the forward vector of the hoverboard, so the forward direction. To do this, just drag the hoverboard in the graph, and from this we can type get forward vector. We have this node here in the transformation category. Let's click on this. So basically this is the forward vector. So to invert this to backward vector, we just need to multiply this by -1. So drag from this here and multiply by -1. So to multiply by -1, we need to convert the second pin here to float. So just right click and click on to float single precision, and now we can put here -1. There we go. So now we have the backward vector of the hoverboard. We just need to apply the backward force in this direction. To do this, we just need to multiply this direction here by the backward force. So just drag the backward force here and connect in the second pin. And now we just need to actually apply this in the hover. To do this, just drag the hoverboard in the graph, and from this, let's type add force. So we have the first node here in the physics, add force. Let's click on this. The force, of course, is this one. And of course, we need to connect the execution pin. So let's connect from the false here. So if we are trying to move backward, we will apply the force in the opposite direction of the forward, right? So this is basically it for the backward. To apply the forward force is basically the same, but I need to do something different here. So let's start by getting the forward force. So let's drag the hoverboard in the graph like so. And from this, let's again get the forward vector. Let's click on this node here. And now let's multiply this with the forward force, right? So let's drag and multiply with the forward force. But I want to apply more force if we are in the ground, and less force if we are in the air. So to do this, let's first convert this second pin here to float. So right click and click on to float single precision like this, and let's drag from this second pin here and let's type select. So we have the select float in the float math category. So let's just click on this, and now we have this node here. So basically we have a boolean input. So if this boolean is true, this node will select the first input here, so the A. And of course, if the boolean is false, this node will select the B input. So for the boolean here, let's use the isGround variable. So let's expand the hoverboard category here, and let's get the isGrounded variable here. Let's connect in the pin. So basically, if we are in the ground, this node will select A. If not, this node will select B. So for the A, we will use the forward force. So let's just drag the forward force here and connect on A. But for B, I will use the same force divided by 5. So let's just drag from the forward force here and let's type divide. So we have the node. And in the second pin, I will put 5 here. And of course, you can tweak those values to make the hoverboard behaves like you want, right? So for me, I will put 5 here. So now let's just connect this on B. So basically, if we are not on the ground, if we are in the air, the hoverboard, this forward force will be less. But if we are in the ground, we will apply the total forward force, right? So now we have the force here. We just need to apply this in the hover. Let me just select those nodes here and let's just put a little bit up like so. Now let's just apply this in the hoverboard. To do so, just drag the hoverboard mesh in the graph, and from this let's drag and type add force. Let's get the node here. Let's connect the execution pin from the true of this branch here. Let's connect the execution pin, and of course the force is this one here. So let's just connect in the force, and there we go. So basically this is the function. Now when we press the keys, this function will apply the force in the correct direction with the correct force, of course. And now we just need to call this function when we press the keys. So to do this, let's go back to the event graph, and here somewhere in the graph, so let me just put here, just right click and type IA move. So we have the input here, the event, right? Click on this. And basically, when we press the keys, the triggered pin will be fired. So let's connect the function on the triggered here. So let's just get the apply movement function. Let's connect the execution pin from the triggered here, like so. And the move input is basically the action value. So let's just drag this on the move input, and there we go. Let's compile and save. And basically, now when we press the keys, we will call the apply movement and we will pass the value that we are pressing, right? Okay, so before testing this, of course, we need to set the acceleration variables. So for me, in the forward acceleration, I will put 10. The backward acceleration, I will put 5. And for the turn acceleration, I will put 150 here. Don't change the forward force, backward force, or turn force. Leave those as 0 because this will hold the calculated force, of course. So now let's compile and save, and let's test to see if this is working. So let's go back to the map so we can test. Let's hit play and let's get on the hoverboard. As you can see, we are hovering, and now if we press the keys, we are moving. So everything is working, and because of the stabilization that we did in the last video, the hoverboard is pretty stable. Even when we hit the wall, as you can see, the hoverboard will always try to balance itself. So even when we jump from high places, so let me just go up here to show you. And if we jump, as you can see, the hoverboard is pretty stable, will always try to balance itself, but the movement is working just fine, so there you go. And I didn't show you this before, but thanks to the limit rotation function, if the hoverboard is upside down, it will correct itself when we try to get on. So let me show you this. Let me just get the hoverboard and let's put it upside down like this. Let me just put up. As you can see, let's hit play. So the hoverboard is upside down. So if we get close here and try to get on, the hoverboard will fix itself, but we have a problem here that we need to solve with the camera. So let me show you this. Okay, so let's go back to the hoverboard blueprint here so I can show you. So basically this is happening because if we select the spring arm, here under the camera settings, we have the inherit pitch, inherit yaw, and inherit row. So basically in this case, we don't need to inherit the row. We don't want to do that. So let's just disable the inherit row. Let's compile and save. And now if we go back and hit play, everything will work. So the hoverboard will correct itself and the camera will be right. So let's get on it. As you can see, everything is working. So basically, even if the hoverboard is upside down, we can still get on it. So that's basically it. And this is basically it for this video. So now we can move the hoverboard around. As you can see, everything is working, the hoverboard is stable. So this is basically it for this video. If you did like this video, please hit the like button and subscribe so you don't lose any new content. And now we have members on the channel, so if you want early access to these videos, feel free to join. I appreciate your support. And as always, thank you for watching, keep learning, I'll see you in the next video.